In this video, I'd like to introduce the psychrometric chart for you. Now, first we need to talk a little bit about a psychrometer. A psychrometer is a device that measures two temperatures simultaneously. It measures a dry bulb temperature and a wet bulb temperature. The dry bulb temperature is what you would normally measure. You take a thermometer and you hold it in the air and it measures the temperature. That's called the dry bulb temperature. A wet bulb temperature is done by simply taking that same thermometer or a identically calibrated thermometer and wrapping it in something like maybe a damp sponge. Okay? Some sort of material that will wick water to the bulb and to the air. So this then, you let that come to equilibrium with the air, and that is going to get you a slightly different temperature, less than the dry bulb temperature. Now if they are the same, then it means you have saturated air or 100% humidity. Okay? The device that measures these two things is a psychrometer. In the old-fashioned way, you would use what's called a sling psychrometer, and that would actually, you would put these two thermometers in a sling that would hold the thermometers to keep them from breaking, and to get them to equilibrium more quickly, you'd moisten a little sponge around the tip of one, and you'd leave the other one dry, and then you would sling them around in the air in circles around you until you felt like it had gotten to equilibrium. Then you would read these two temperatures. And it's a very simple way of being able to then predict, well, calculate all of these other values associated with humidity that we've been talking about. This sort of data has been graphed, and over the years people have come to use, maybe not love, but use a psychrometric chart. Okay, so psychrometric means that it's measuring this dry bulb and wet bulb temperature and relating it to humidification. So, in your textbook, pages 994 to 995, these tables are in SI and English units at 1 atmosphere pressure, and it's basically going to be good for problems that are near atmospheric. So the sorts of things that a weatherman might report on. So the kinds of temperatures that you would experience, in your life that you would be walking through. It's not going to be good for things like, oh, I'm going to put something in an oven, okay? Because a weatherman is never going to experience something at those kinds of temperatures. So we're going to have a limited range when this is useful, but it is such a useful device that it's important that you learn how to read these. Now there's a lot of information on this chart, and so let's go through this and look at it. So I have a very simplified drawing here that has just a few of the lines on it, and then we'll look at an example and look at a more traditional chart with a lot of little lines on it, but they'll all have the same shape. So first of all, the dry bulb temperature. The dry bulb temperature is what people refer to as the temperature. Okay? The dry bulb temperature, the markings for this are going to be across the bottom of the chart. And you'll read a number here, so maybe you read, 30 degrees. And you find it here, and everything straight up and down is going to represent that 30 degrees. Okay? Over here maybe is 50 degrees, and straight up and down is going to represent 50 degrees. My axis over on the right side has humidity ratio. Okay? The omegas that we've been talking about. It's the mass of water vapor per mass of dry air. And so those are across here, and again, once you find your value here, you'll read straight across, left, right, to find everything that has that constant value of humidity. Relative humidity, which is the one that you hear most often in a weather forecast, these are going to be these curves that sweep across the graph. So 100% relative humidity is the top sweeping curve, and the others will have a similar shape, just lower, going down to matching the dry bulb temperature, which is a 0% relative humidity. So you'll find one of these, the markings will be near the curve, and just follow the curve along, and that's a constant relative humidity line. Next, let's talk about the wet bulb temperature. Okay, wet bulb temperature and the dew point temperature both are the same curve. They're the temperatures that go along this top edge. Okay, if I'm talking about the wet bulb temperature, I'll follow lines that go off this direction here. If I'm talking about saturation, well, that means I'm talking about 100% relative humidity, so those will be the same. Okay, but so I'll have wet bulb temperatures. I'm going to read the numbers up along this axis, and a constant wet bulb temperature line will go off at this angle, about -40 degrees. Now up here, there's an extra little axis. It's the scale for the enthalpy of the mixture. It's done as a per mass of bone dry air or dry air, okay? But it's the enthalpy of the mixture. And so I'll take those, once I follow this line up here, this will tell me what the enthalpy is at saturation. And then I'm going to find an enthalpy correction line that's going to be sort of curved lines, and we're going to see that in an example in a few minutes. Those are kind of curved lines, and they will correct for if I'm not at saturation. Wet bulb and, no, that's not what I wanted. I'm sorry, specific volume. I was reading that. Okay, specific volume of my mixture is going to be on lines. There are not very many of them. You're going to see that they're about here and here and here. So when you need to estimate those, you're going to do some pretty broad estimation. But these are just tilted slightly off vertical. But these are going to be constant volume. And usually the values are read kind of along the line, but typically down in this area, but just kind of randomly scattered numbers. So let's look at an example. Okay, so here was a weather forecast that I found, you know, at the time when I was doing this video, this was the value that I found. Okay, 14 degrees C, relative humidity is 32%. I actually got a lot of other information off of this. Some of this we'll use to confirm. For instance, the dew point was -2. So we can come in and we can confirm some of these things later. But let's just see what we're able to do with this. Now first I'm going to go through this using the definitions, and then we're going to do it using the psychrometric chart. So using the definitions, I have, this is my given data, okay, and I was able to find things like the mole fraction, okay, the dew point temperature, and the humidity ratio or specific humidity. The way I was able to find these things was, okay, first of all, I used Antoine's equation at the lower temperature ranges for calculating vapor pressure. And relative humidity says that I need the vapor pressure at the given temperature, so at 14 degrees C, which I came up with 0.01597 bar. And I needed to know what the vapor pressure was of my mixture. Now, I have 32% relative humidity. Take the 32% and multiply it by the actual pressure. That product will be the partial pressure of the water vapor. Okay? I can calculate the mole fraction then from the partial pressure. That's Y times the total pressure. Okay? We got that. To find the dew point, I'm looking for when the relative humidity is 100%. So that means that the vapor pressure is the same as the the saturation pressure. And I found that value as a -2 degrees C, which matched over there. To find the humidity, I just need to take my mole fractions and convert over to mass fractions. And using molecular masses, I assumed a basis of 100 kilomoles of dry air. BDA is bone dry air. It's just a convenient way for me to write that it's dry air. It's something that I picked up when I was in school. So BDA is bone dry air. If I assume 100 kilomoles of bone dry air, and I know the mole fraction, then that will allow me to calculate the mass of water and the mass of bone dry air. And that allows me to calculate the absolute humidity. But now we really want to focus on learning to use the psychrometric charts. Now, mole fractions are not something that you can really get off of a psychrometric chart. But I can find all of these other values. And so let's look at the chart. So if I switch my view to, okay, it's not going to let me. There we go. View. I want to zoom to 75% so we can look at the graph a little bit better. Okay. So I had a temperature of 14 degrees C. So that's my blue line right here. And I knew a relative humidity, and that's this blue curve. Okay. Where those two cross is my actual physical condition. If I want to read the absolute humidity, I read across and read the number over here. If I want to know the saturation temperature, then I'm going to read across these lines, these angles over here. This is the saturation temperature. If I continue on out, this is the saturation enthalpy. These lines across here are my enthalpy deviation curves. Okay, you can find it. It's written right there. And so this maybe has a saturation enthalpy of, it looks like about 22. But it's actually, based on this, 0.1 smaller than that. So I would subtract 0.1 from my answer. Using this, you can get out a chart and follow along and see what else you come up with. But I came up with 21.7. Actually, I got ridiculously 715. I'd say 21.7 kilojoules per kilogram of bone dry air. This humid volume, using these lines across this way, I got about 0.82 meters cubed per kilogram. And the wet bulb temperature of 5.5. So again, try these on a graph of your own and see if you too can read these values. And then we'll come back and we'll work a problem using these in the next video.